Alright, so in this video we're going to revisit electron configuration, but take a little bit more of a logical approach to hopefully connect some of the dots. So today in class, we talked about how we made a transition from the orbits of Bohr's model to the orbitals within quantum theory. And we talked about how we can use the 4 quantum numbers to describe each of those orbitals. So let's just take for an example, if we start out on the very first energy level, so that would be as if we had the principal quantum number equal to 1. So within the first energy level, the only possible subshell there is the S subshell. And within the S subshell, there's only one orbital. So here's our energy level, our subshell, and then the orbital within the subshell. Now we learned that each orbital, kind of like the rooms of our houses, can only hold 2 electrons. So the way we're going to denote electrons as we go throughout is using half arrows. And so whenever 2 electrons occupy the same orbital, one should be spin up and one should be spin down. Now, let's consider what happens when we move to the second energy level. So in the second energy level, we have the S subshell with 1 orbital, but then we now add on the P subshell, and that happens to have 3 different orbitals. Okay, so now if we consider again, we know that each orbital can hold 2 electrons. So I'll place 2 in this orbital, and then in each of these orbitals, according to Hund's rule, we should place electrons by themselves in the orbitals before pairing them with another electron. So I'll give each orbital 1 electron first, and then go back and pair it with another electron. So if you'll notice, again, this is the second energy level, and the second energy level happens to contain the S subshell and the P subshell. Within the S subshell, there's only 1 orbital. But however, within the P subshell, there are 3 orbitals, and each individual orbital can hold a total of 2 electrons. Now let's keep going to the third energy level. We'll talk about how these connect to electron configuration in just a second. So in the third energy level, the S subshell is present with its 1 orbital. The P subshell is present with its 3 orbitals. And then the D subshell is present with its 5 orbitals. Now, instead of trying to write out or draw each of the 4-leaf clovers for the D, I'm simply going to represent an orbital with just 1 small line there. So this will be an orbital, this will be an orbital, this will be my 3rd orbital, my 4th, and my 5th. So the S subshell has 1 orbital, the P subshell has 3 orbitals, and the D subshell has 1, 2, 3, 4, 5 orbitals. So just like we did before, we know that each orbital can hold 2 electrons. So within the S orbital, I can place 2 electrons. And then within each P orbital, I will be able to place 2 electrons. 1 here one here, one here, and then adding a second one. Okay. Now notice, just like I did for the D, I could have represented these orbitals as just lines. I just happen to draw them out since they're a little easier to draw. So now let's do the same for the D orbitals. So the D subshell has 5 different orbitals, each of which can hold a total of 2 electrons. So when we take 5 orbitals multiplied by 2 electrons, that gives us a total of 10 electrons that can be within the D subshell. So let's add those in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Alright. So now let's take a step back and look at where the electrons actually ended up. So let's return to the first energy level. So here, this happens to be the first energy level in the S subshell. Now, within this S subshell, there's one orbital, and it can hold 2 electrons. So total in this 1s subshell, it's holding 2 electrons. So note how I'm noting the energy level, the subshell, and then the number of electrons that can fit within that subshell. Let's do it again. So if we consider the second energy level, we now have the S subshell that's on the second energy level. So I'll denote it with a 2, and this is the S subshell. And again, if we look at the electrons present, we count and see that there are 2 electrons present for that subshell. And I'll just trace over this one to make it a little more visible. Now, let's move over and consider the P subshell. So again, we're still working with the second energy level and with the P subshell. But now if we look, we have filled the subshell with 6 different electrons because there are 3 orbitals that can each hold 2 electrons, and 3 times 2 is 6. So we could say that this is the 2p subshell that's been filled with 6 electrons. Now we could continue to do the same thing. We could call this 3s2. This we could call the third energy level, the p subshell, and this is housing 6 electrons. Now with the D, still the third energy level, but this time it's the D subshell, and in this case it happens to be housing a total of 10 electrons. Now let's look at this case. What if we were still in the third energy level in the D subshell? So let me draw my orbitals. But what if we only had 5 electrons? That means our D subshell is not completely filled. So in this case, we could denote this as being the third energy level, the D subshell, and it contains 5 electrons. So basically what we've been doing so far is taking these subshells within an energy level and filling them with electrons. And the little notation we've been writing denotes the energy level, the subshell, and then the number of electrons that that particular subshell can hold. Again, just for example, the P subshell, when completely filled, can hold 6 electrons. That's due to it having a total of 3 orbitals at 2 electrons each, so 3 times 2 is 6 total. So that's all we're noting, is that within this 3p subshell, there are 6 electrons. Now, it just so happens that the number of electrons within each subshell happens to correspond to the periodic table. So what I've done is I've colored the different sections of this periodic table to go along with the different subshells. The first 2 columns are S. Our last few columns, starting with boron and going over to neon, correspond to P. Our middle transition elements correspond to D. And our bottom series of lanthanides and actinides correspond to F. And basically this arrangement is going to give us a key for how we show where the electrons are within the subshells of an atom. So if you'll notice, if we think back to our S subshell, whether that was in the 1s, the 2s, or the 3s, each time our S subshell can only hold a maximum of 2 electrons. And if you'll notice, if we kind of consider helium as being part of the S block, that for every energy level, there are 2 elements. So, these are going to correspond with the 2 electrons that we find within our S subshell. If an element falls in this column, then it only has 1 electron placed within the S subshell. But if it falls within the second column, then it will have 2 electrons placed within the S subshell. So let's do an example, and sometimes it takes time to kind of see the pattern. So let's just start out with hydrogen. So if we look at its location on the periodic table, we'll notice that it corresponds to the first energy level, and it's also within the S block. Now we've already noted that within the S subshell, just like before, we can only have a maximum of 2 electrons. Now if we consider hydrogen is in this first column, so it only has 1 electron within the S subshell. But now let's consider what happens when we move over to helium. Helium is likewise in the first energy level in the S subshell, but now it has a total of 2 electrons placed within that particular subshell. So we're going to denote this as 1s2. So the only difference is that helium has 1 more electron than hydrogen, and so it's able to have a completely filled S subshell. Now, let's move down to our next 2 elements on the periodic table, lithium and beryllium. So, basically,